So far we have discussed the situation for silicon, which is an element with 4 valence electrons. Carbon and germanium are elements which have 4 valence electrons as well. Carbon has 4 valence electrons filling the second shell, and germanium has 4 electrons partly filling the fourth shell. Carbon, silicon and germanium all have tetrahedral coordination and form a diamond cubic crystalline lattice in its crystalline phase. Silicon and germanium can be considered as 4 semiconductor materials. The 4 stands for the number of valence electrons of the element. Why is carbon not a semiconductor, as it has the same lattice? To answer this question, we have to consider the bond length between the atoms. Or in other words, to which extent the neighboring orbitals forming the molecular orbital are pressed together. The bond length is in general expressed in terms of lattice constant. What is the relation of the lattice constant and the bond length of a diamond cubic crystalline lattice? In this figure, the unit cell of a diamond cubic crystalline lattice is shown. The edge length of the cube is equal to the lattice constant. In a diamond crystalline lattice, the lattice constant equals 4 times the silicon-silicon bond length divided by the square root of 3. In the next graph, we plot the band gap of crystalline carbon, silicon and germanium versus the lattice constant. Crystalline carbon is another name for diamond. We indeed see that the band gap is very large for diamond, as diamond has the smallest lattice constant. In a very simplified representation, the larger band gap can be considered as a larger overlap of the original sp3-like orbitals of the neighboring atoms. A larger overlap induces a larger splitting of the energy levels of the bonding and anti-bonding levels. Materials with semiconductor properties can be made from other materials than elements with 4 valence electrons as well. Let's consider the so-called 3,5 semiconductor materials like gallium arsenide. 3,5 semiconductor materials consist out of 2 elements. One element has 3 valence electrons. The other element has 5 valence electrons. These materials can, similar to silicon, form a diamond cubic crystalline lattice. In the crystalline lattice shown here, the gallium are the blue atoms and the arsenide are the red atoms. The difference with silicon is that every gallium atom is neighboring 4 arsenide atoms, and the other way around, every arsenide atom is neighboring a gallium atom. Let's consider the 3,5 materials based on gallium, like gallium phosphor, gallium arsenide, and gallium stibbium. Again, the larger the lattice constant of the material, the smaller the band gap will be. Gallium phosphor has the smallest lattice constant and therefore the largest band gap. Another group of semiconductor materials are the so-called 2,6 semiconductor materials like cadmium telluride. 2,6 semiconductor consists out of 2 elements. One element has 2 valence electrons, the other element has 6 valence electrons. These materials can form a diamond cubic crystalline lattice as well. In the crystalline lattice shown here, the cadmium atoms are the blue atoms and the tellurium atoms are the red atoms. So every cadmium atom is bonded to 4 tellurium atoms, and the other way around, every tellurium atom is neighboring a cadmium atom. Let's consider the 2,6 materials based on cadmium, like the cadmium sulfur, the cadmium selenium, cadmium tellurium. Again, the larger the lattice constant of the material, the smaller the band gap will be. Cadmium telluride has the largest lattice constant and therefore the smallest band gap. I hope you have become familiar with the important properties of semiconductors like the valence band, conduction band, and band gap and its relation to the molecular orbitals of the elements that make the semiconductor material. And I have shown that we have different semiconductor materials like silicon, germanium, gallium arsenide, and cadmium telluride. Important to remember is that all these semiconductors have different band gaps. So, how can we make semiconductor materials conductive? Or in other words, how can we fill the conduction band with free electrons? It's my pleasure to show that in the next video lecture.